Good morning and welcome to Lecture 10. This is our second of 4 lessons about calculus. This week we're going to discuss differentiation rules, derivatives of trigonometric functions, and the chain rule. Let's start by talking about some differentiation rules. Last week I introduced the idea of the derivative as the slope of a graph. And we saw that we could use the definition involving the limit to calculate that slope. But often there's an easier way. Often we want to use the differentiation rules. We start with the rule for a constant function. If k is a number, the derivative of k is 0. The slope of a constant function is equal to 0. For a power function, that's a function x to the power n for a real number n, the rule is that the derivative of x to the power n is n multiplied by x to the power n minus 1. So for example, the derivative of x cubed is 3x to the power 3 minus 1 or 3x squared. Two more examples. We can use this rule to differentiate the square root of x. Why? Because square root of x just means x to the power of a half. So we can use our rule. The derivative of x to the power n is nx to the power n minus 1. So we have n, that's a half, x to the power n minus 1, or half minus 1. That's a half, x to the power minus a half. Go back to using a square root. X to the power minus a half means 1 divided by square root of x. So the answer is 1 divided by 2 square root of x. Or we could use that to differentiate 1 divided by x to the power 4, because 1 divided by x to the power 4 just means x to the power minus 4. So again, we have x to the power n, but now n is equal to minus 4. So we use our rule, nx to the power n minus 1. Minus 4, x to the power minus 4 minus 1. That's minus 4x to the power minus 5, or we could write that as minus 4 divided by x to the power 5. Our next rule is called the constant multiple rule. That's the rule we use if we have a function multiplied by a number. If u is a differentiable function and if k is a number, then the derivative of ku is equal to k multiplied by the derivative of u. What this means is if we have a number, in this case k, inside a derivative, we're allowed to take the number outside of the derivative. And this one I want to prove. How do we prove it? We prove it using the definition of the derivative. By definition, the derivative of ku is the limit as h tends to 0 of, and then we have our function ku at x plus h minus our function ku at x, all divided by h. But we had a constant multiple rule for limits. If we have a number inside a limit, we're allowed to take the number outside of the limit. So that's just the same as k multiplied by the limit as h tends to 0 of u at h plus x plus h minus u at x divided by h, or k multiplied by du dx. You don't necessarily need to know the proof, but you'll need to know this rule. For example, the derivative of 3x squared, we're allowed to take the number 3 outside of the derivative, so that's 3 ddx of x squared, 3 times 2x or 6x. And we do the same thing with minus signs, because minus u just means minus 1 multiplied by u, and minus 1 we're allowed to take outside minus 1 multiplied by du dx, or minus du dx. The sum rule. What do we do if we have two functions added together? If u and v are differentiable functions at a point x0, then their sum, u plus v, is also differentiable at this point x0, and the derivative of u plus v is the derivative of u plus the derivative of v. So say that another way, anytime we have the derivative of two functions added together, we're allowed to cut just here into two different easier or smaller derivatives. So for example, differentiate y is equal to x cubed plus 4 over 3x squared minus 5x plus 1. I have four functions here added together or subtracted, but don't worry about the minus sign. We've looked at minus signs already. At the plus, we're going to cut. We're going to cut at this minus sign, and we're also going to cut at this plus. So we're cutting our function in derivative of our function into four smaller and easier derivatives. Derivative of x cubed plus the derivative of 4 over 3x squared minus the derivative of 5x plus the derivative of 1. The derivative of x cubed is 3x squared. The derivative of x squared is 2x, so that means we multiply it by 4 over 3, we get 8 over 3x. The derivative of 5x is 5, and the derivative of a constant function, the 1, is just 0. Does the curve y is equal to x to the power 4 minus 2x squared plus 2 have any points where the derivative is equal to 0? And if the answer is yes, where are they? What we're going to do is we're going to differentiate this function, and then we're going to put it equal to 0, and we're going to see, are there any points which make the derivative equal to 0? So step 1, let's differentiate this function. The derivative of x to the power 4 is 4x cubed. The derivative of 2x squared is 4x, and the derivative of 2 is 0. Using the rules we've done already, the power rule, the constant multiple rule, and the sum rule, we find that this is 4x cubed minus 4x, which I then want to factorize. Both terms have 4x in, take that off, 4x, x squared minus 1, but then x squared minus 1 is the same as x minus 1 multiplied by x plus 1. Now, how can we make this equal to 0? Well, it's 0 if x is 0. It's 0 if x is equal to 1, because then x minus 1 is 0. And it's also 0 if x is equal to minus 1, because then x plus 1 is equal to 0. And those are the only ways that this can be equal to 0. So the answer is yes, there are 3 points where the derivative is equal to 0, and they are x is minus 1, 0, and 1. If I show you the graph, you can see that this is true. There's 3 points where the slope of the graph is equal to 0. Our next rule is called the product rule, and that's the rule we use if we have two functions multiplied together. If ux and vx are differentiable at a point x0, then their product, u multiplied by v, is also differentiable at this point x0. And the rule is that the derivative of uv is equal to u multiplied by the derivative of v plus v multiplied by the derivative of u. Or if we use prime notation, the derivative of uv is u prime v plus uv prime. So what this means is, of our two functions, we need to differentiate one of the functions and leave the other one as it is. And then we do plus, and then we do the other one. we differentiated u first, then in the second term we differentiate v, but we leave u as it is. So for example, differentiate y is equal to x squared plus 1 multiplied by x cubed plus 3. And I'm going to solve this in two different ways. First, I'm going to use the product rule because our function is u multiplied by v. We have a function multiplied by a function. We have the function u is equal to x squared plus 1 multiplied by the function v is equal to x cubed plus 3. So using the product rule, dy dx is, we differentiate the first function, leave the second function as it is, then do plus, leave the first function unchanged, and then differentiate the second function. The derivative of x squared plus 1 is 2x plus 0, and the derivative of x cubed plus 3 is 3x squared plus 0. Multiply all this out, and I'll leave that for you to check. We end up with 5x to the power 4 plus 3x squared plus 6x. Now I'm going to solve this problem a different way, and you'll see we get the same solution. Another way to solve this problem would be to first multiply the brackets out. I'll leave it for you to check that y is the same as x to the power 5 plus x cubed plus 3x squared plus 3. And then differentiate this, we get 5x to the power 4 plus 3x squared plus 6x plus 0, which of course is exactly the same answer that we got before. The quotient rule. This is the rule we want if we have function divided by function. If u and v are differentiable at a point x0, and this time we need to be a little bit careful, as long as v as x0 is not 0, because we don't want to be dividing by 0, then u divided by v is also differentiable at x0, and the rule says this. The derivative of u divided by v is u prime v minus uv prime divided by v squared. Now, I'll just remind you of the product rule at the bottom. The product rule said the derivative of u multiplied by v is u prime v plus uv prime. In the quotient rule, we have a minus sign instead of a plus, and then we divide by v squared. Another thing I want to say is in the product rule, it doesn't matter if we differentiate u first or differentiate v first because we've got a plus in the middle. But in the quotient rule, we have a minus sign. So it does matter that u is differentiated first on the top, and then minus, and then uv prime. For example, differentiate t squared minus 1 divided by t cubed plus 1. This time we have function divided by function. We have u divided by v, where the function on the top, u, is t squared minus 1, and the function on the bottom is v equal to t cubed plus 1. So we're going to be using the quotient rule. Our derivative, dy dt, is u prime v minus uv prime divided by v squared. So first we differentiate u, derivative of t squared minus 1, and we leave v as unchanged, leave v as it is, and then minus, leave u as it is, and then we differentiate v, derivative of t squared cubed plus 1, And then everything is divided by v squared. Everything is divided by t cubed plus 1 squared. Derivative of t squared minus 1 is 2t. Derivative of t cubed plus 1 is 3t squared. And after that, it's just simplifying our function until we get to our final answer. Differentiate f of s is equal to square root of s minus 1 divided by square root of s plus 1. Again, we have function divided by function. Now, the function on the top is u is equal to the square root of s minus 1, and the function on the bottom is v equal to the square root of s plus 1. And let me remind you that we've already seen that the derivative of the square root of now s is 1 divided by 2 square root of s. So, first of all, quotient rule formula. df ds is u prime v minus uv prime divided by v squared. And then we're going to put in everything that we need to put in. First, u prime, derivative of root s minus 1, and then v minus u v prime divided by v squared. Derivative of the square root of s is 1 over 2 root s, and the derivative of minus 1 is 0. So just 1 over 2 root s here, and also 1 over 2 root s just here. Simplify everything down, and we get our final answer, which I'll leave for you to check. 1 divided by root s, open bracket, root s plus 1, close bracket, squared. Let's talk about second order derivatives. If y equal to f of x is a differentiable function, then f prime of x is also a function. If f prime is also differentiable, then we can differentiate it again to find a new function which we call f double prime. F double prime is called the second derivative of f, and we can write it in these ways. I could write f double prime of f double prime of x, or d dx of f prime x, or d dx of dy dx, or d squared y dx squared, or dy prime dx, or y double prime. These all mean the same thing. For example, if y is equal to x to the power 6, then y prime is the derivative of x to the power 6, or 6x to the power 5, and y double prime, that's the derivative of y prime, or the derivative of 6x to the power 5, is 30x to the power 4. Or we could write this calculation in one line. 2 derivatives of x to the power 6 is the derivative of x to the power 6, that's the derivative of 6x to the power 5, or 30x to the power 4. And we also have higher order derivatives. If y double prime is differentiable, then its derivative y triple prime is the third derivative of f. If y triple prime is differentiable, then its derivative is the fourth derivative of f. If the fourth derivative of f is differentiable, then its derivative is the fifth derivative of f, and so on. Now, you'll note here that for the first 3 derivatives, we're using prime notation, but then after we get to the number 4, we change to open bracket 4, close bracket. Why? Well, imagine we wanted to do, let's say, 13 derivatives of f. If we use prime notation, then we would have f prime, 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 prime. But that would just be silly. Makes more sense when we get to the higher numbers to use numbers in brackets. For example, find the first four derivatives of y is equal to x cubed minus 3x squared plus 2. First derivative, y prime is 3x squared minus 6x. Second derivative, differentiate again, 6x minus 6. Third derivative, differentiate that, we get 6. Fourth derivative, 0. Because the derivative of a constant function, in this case 6, is 0. Now, note that we were asked for only the first four derivatives, but at this point we can see that because the derivative of 0 is 0, all of the derivatives for n higher than 4 are also going to be equal to 0. My second chapter for today's lesson is about the derivatives of trigonometric functions. Let's start with sine and cosine. The rules to remember are that the derivative of sine x is cosine x, and the derivative of cosine x is minus sine x. So for example, if I wanted to differentiate x squared minus sine x, I can use the sum rule of derivative of x squared minus the derivative of sine x. So 2x minus cos x. I could differentiate x squared sine x using the product rule. Differentiate the first function, differentiate x squared, but don't change sine x, plus, and then don't change x squared and differentiate sine x. 2x sine x plus x squared cos x. Differentiate y is equal to sine x divided by x. This is a quotient rule question. We have function divided by function, so we use the quotient rule. Differentiate sine x, but then don't change, multiply it by the function on the bottom, just x, minus, and then leave sine x unchanged and differentiate the function from the bottom, derivative of x, and then it's all divided by x squared. You can check that we get x cos x minus sine x divided by x squared. Differentiate 5x plus cos x. We get 5 minus sine x. Differentiate y is equal to sine x cos x. Product rule question because we have function multiplied by function. So differentiate sine, leave cos as it is, plus leave sine as it is, and differentiate cos. Cos squared x minus sine squared x. Differentiate y is equal to cos x over 1 minus sine x. This is a quotient rule question. So we start with u prime v minus uv prime divided by v squared. That's derivative of cos x multiplied by 1 minus sine x minus, and then cos x, derivative of 1 minus sine x, all divided by 1 minus sine x squared. Derivative of cos x is minus sine x, and the derivative of cos x is, the derivative of 1 minus sine x is 0 minus cos x. And this we need to simplify. Multiplying it out, we have minus sine x plus sine squared x plus cos squared x. And everybody remembers from school, sine squared plus cos squared is equal to 1. So look what we have. We have 1 minus sine x divided by 1 minus sine x squared. Cancel 1 minus sine x on the top with one of the ones on the bottom, and we're just left with 1 divided by 1 minus sine x. And after we've simplified it as much as we can, we get to our final answer. The tangent function. The derivative of tan x is equal to sec squared x. I want to prove this. We can prove this using the quotient rule because tan just means sine divided by cos. And we know how to differentiate a function divided by a function. We just use the quotient rule. So that's derivative of sine multiplied by cos x minus sine x multiplied by derivative of cos x, all divided by cos squared x. And after we've done our derivatives, look, we have cos squared plus sine squared on the top, but that's just 1. We get 1 divided by cos squared x, and that's exactly the same as sec squared x. The other three. The derivative of sec x is sec x tan x, the derivative of cotan x is minus cosec squared x, and the derivative of cosec x is minus cosec x cotan x. It's possible to prove all three of these using the quotient rule, just as I did in the previous one when I proved that the derivative of tan x is sec squared x. I encourage you to practice these because sometimes we ask these in an exam, sometimes we don't. I haven't written the exam this year yet, so I haven't decided whether to ask this or not. But just in case I do ask it, I encourage you to practice these proofs beforehand. Find y double prime if y is equal to sec x. Well, differentiate it once. The derivative of sec is sec x tan x. To get y double prime, we need to differentiate it a second time. We need to differentiate sec x tan x. But that's function multiplied by function, so we need the product rule. Derivative of sec x multiplied by tan x plus sec x multiplied by derivative of tan x. Derivative of sec x is sec x tan x. Derivative of tan x is sec squared x. We obtain the answer sec x tan squared x plus sec cubed x. And the third and final chapter for today's lesson is about the chain rule. How do we differentiate things like this function? F of x is sine of x squared minus 4. Sine is a function, we know how to differentiate that, and x squared minus 4 is a function. We know how to differentiate x squared minus 4, but here we have a function of a function. And the answer is we use a rule called the chain rule. So first of all, let's suppose we've got two differentiable functions, f and g. Then f composed with g is differentiable, and the formula is the derivative of f composed with g is the derivative of f calculated at g of x multiplied by the derivative of g. Now that might be easier to remember if we use Leibniz's notation. If we use Leibniz's notation, the chain rule says dy dx is equal to dy du du dx. And this is the notation I like to use because even though dy du doesn't really mean dy divided by du, we might pretend that it does, and then we can pretend that we can cancel out the du's. So for example, differentiate y is equal to sine of x squared minus 4. Here we have a function of a function. We have y is equal to sine u, where u is x squared minus 4. And we know how to differentiate each The derivative of sine u is cos u, dy du, differentiate with respect to u, is cos u, and du dx, the derivative of u with respect to x, is 2x. So then we can use the chain rule, which says dy dx is dy du, du dx, cos u multiplied by 2x. But we're not finished yet because we still have a u here. We don't want to have a u in our final answer. The final step is to replace the u by the x squared minus 4. The final answer is that dy dx is 2x cos x squared minus 4. Let's do another one. Differentiate sine of x squared plus x. The first thing we need to do is we need to choose a u. So I'm going to look at my function. I see I have an x squared plus x here. I'm going to choose that for my u. I'm going to start by saying let u be x squared plus x. And then I'm ready to do the calculation. Because by the chain rule, d dx of sine of x squared plus x is the same as d du of sine u multiplied by du dx. And then we just have two easy derivatives to calculate. The derivative of sine u is cos u, and the derivative of x squared plus x is 2x plus 1. Replace the u by x squared plus x, and we get our final answer, 2x plus 1 multiplied by cos x squared plus x. In mathematics, anytime we use a rule in our calculation, we should say the rule that we use. Here I've used the chain rule, so if this is a perfect answer, if I want to get all of the points in the exam, I need to write something like by the chain rule in my answer. In an exam, there's probably 1 point or 2 points just for writing by the chain rule, if this was your question. Sometimes we need to use the chain rule 2 times. For example, differentiate g of t is equal to tan of 5 minus sine 2t. Well, let's start the way we did before. Look at the function and choose the u. I'm going to choose u is 5 minus sine 2t because then I just have g of t is equal to tan u. And I know how to differentiate tan u. By the chain rule, dg dt is dg du du dt. Derivative of tan is sec squared, so I get sec squared u multiplied by du dt. That's the derivative of 5 minus sine 2t. Now at this point, I need to use the chain rule a second time. I've already used the letter u in this answer, so now I'm going to need to use a different letter. Use any letter that you want, A, B, C, D, whatever you want. I'm going to use the letter W. I'm looking at my derivative and I see there's a 2t just here. So I'm going to let W be equal to 2t. And I'm doing that so that d dt of 5 minus sine 2t, or d dt of 5 minus sine w, by the chain rule is the same as ddw of 5 minus sine w dw dt. And at this point, everything is an easy derivative, so we can write down the derivative of 5 minus sine w is minus cos w, and dw dt, the derivative of 2t is just 2. Simplify our answer and we get minus 2 cos 2t sec squared 5 minus sine 2t. The question started with just G and T, so our final answer should just be G and T. Your final answer should not have a U or a W in it. We should just have the variables that we started with. And finally, well, almost finally, let's talk about powers of a function. This is a special version of the chain rule, which is useful. Let me just remind you, the chain rule says dy dx is equal to dy du du dx, as long as we have two differentiable functions. If y is equal to f of u, then that's the same as saying that d dx of f of u is f prime of u du dx. Okay, so this is what we've got so far. And that will work for every differentiable function, f. Now let's look at just power function. Instead of looking at every possible function f, let's just look at f of u is equal to u to the power n. Because then we know that f prime of u, the derivative of f with respect to u, is n u to the power n minus 1. So our chain rule formula becomes d dx of u to the power n is n u to the power n minus 1 du dx. The next few examples are going to be using this formula in the box. For example, differentiate 5x cubed minus x to the power 4 all to the power 7. So we have a function u to the power 7, and then we want to differentiate it. Really, we're doing d dx of u to the power 7 here. And we know that 7 u to the power 6 multiplied by du dx. So 7 u to the power 6, 7 5x cubed minus x to the power 4 to the power 6, multiplied by du dx, multiplied by d dx of 5x cubed minus x to the power 4. And I'll leave the final answer for you to check. Another one, differentiate 1 over 3x minus 2. But that's just the same as saying differentiate 3x minus 2 all to the power minus 1. By the chain rule, if we're going to differentiate u to the power minus 1, with respect to x, it's going to be minus 1 u to the power minus 2 multiplied by du dx. And that's what we have, minus 1 u to the power minus 2 multiplied by du dx. We get our final answer, minus 3 divided by 3x minus 2 squared. Differentiate sine to the power 5x. We have u to the power 5, and we're going to differentiate it. 5u to the power 4 multiplied by du dx, multiplied by the derivative of sine x, which is cos x. Differentiate the absolute value of x. Well, I'm starting by saying that the absolute value of x squared is the square root of x squared. Let's think about this for a moment. The absolute value of 3 is 3, and 3 squared, and then take the square root, that's square root of 9, or 3, so that works. What if we do minus numbers? Let's say minus 3. Absolute value of minus 3 is 3. If I do minus 3, I square it first, and then I take its square root. Then again, I'm doing square root of 9, which is 3. Okay, so that makes sense. Absolute value of x is the same as the square root of x squared. So the derivative of the absolute value of x is the same as the derivative of the square root of x squared. If we let u be equal to x squared, then we're doing d dx of the square root of u. By the chain rule, that's the same as d du of the square root of u multiplied by du dx, d dx of x squared. We obtain x divided by the square root of x squared, or x divided by absolute value of x. Another one. Let y be 1 divided by 1 minus 2x cubed, as long as x is not a half, because we don't want to divide by 0. Show that dy dx is always strictly greater than 0. Well, first I'm going to calculate this derivative, and then I'm going to show that this is always greater than 0. So I start with dy dx, that's d dx of 1 minus 2x to the power of minus 3. That's the same as doing d dx of u to the power of minus 3. And so using the chain rule, we know that's minus 3, u to the power minus 4, decrease the power by 1 from minus 3 to minus 4, and then multiply it by du dx. So minus 3, and then u to the power minus 4, 1 minus 2x to the power minus 4, multiplied by du dx, multiplied by d dx of 1 minus 2x. And then after we've simplified that, you can check that we get 6 divided by 1 minus 2x to the power of 4, as long as x is not a half. Now the function on the bottom, 1 minus 2x to the power of 4, that's always strictly positive. Any non-zero number to the power of 4 is always strictly positive, and 6 is positive. So we've got positive number divided by positive number, that's positive number. So we can see that dy dx is always strictly positive. And I want to finish today's lesson by answering the question, why do we use radians in calculus? Well, let me remind you that the formula we've been using, d dx of sine x equal to cos x, this is true only if we use radians. So what happens if we use degrees? Well, what do radians and degrees mean? Look at this semicircle. The angle inside a semicircle is 180 degrees. And if the semicircle has radius 1, then the distance around the outside is pi. So from this picture, we can see that 180 degrees is the same as pi radians. Divide both sides by 180. 1 degree is the same as pi divided by 180 radians. Multiply both sides by x. X degrees is the same as pi x divided by 180. So if we wanted to do the derivative of sine x degrees, what we're really doing is the derivative of sine pi x divided by 180. And by the chain rule, that's pi divided by 180 cos pi x over 180, or pi over 180 cos x degrees. So that leaves us with two formulae. If we use radians, we have the nice formula. The derivative of sine is equal to cos. If we want to use degrees, we would have this formula which is not as nice. The derivative of sine x degrees is pi over 180 cos x degrees. And if we were doing lots of derivatives in our calculation, we'd end up with lots of pi's, lots of 180s, and the calculation would become a mess. This is why we use radians in calculus, so that we can use this nice formula for derivative of sine and similarly a nice formula for the derivative of cos. And that is the end of this week's lesson. Next week is the third of our 4 lectures about calculus. We're going to start going backwards. We're going to do antiderivatives. Those will be the opposite of derivatives. And then we'll move on to talking about integration and the definite integral. Are there any questions?